So let me introduce Francesco Volpe, who is the CEO of Renaissance Fusion. And yeah, you can find his video on the Indico page. I will not take much time on this, but I would like to introduce directly Francesco so he can tell us what the concept of Renaissance Fusion is and what you are working at the moment in the fusion field. So Francesco, the floor is yours.
Yeah, thank you very much. And let me turn on the camera. I hope you can see me. This is just to say hi to everybody. And yeah, I'm in an hotel in Madrid with poor internet. So for the rest of my presentation, I will turn the camera off, share my screen. 1 second, please bear with me. And I will start. So yes, we're getting there. Here we go. All right, so yeah, I'm presenting. So this is actually, this is the first time I'm publicly presenting our new logo shown here and our new branding. There will be a launch of a new website on the 30th of November. So please do visit that website, stellarator.energy, shown here at the bottom, and check for job opportunities and student project opportunities, or email me at this email here. So in this brief presentation today, I will describe the motivation for Renaissance Fusion, our 3 technological pillars, temperature superconductors, liquid metals, and stellarators, and talk about next steps, including indeed student opportunities. So about the motivation. So this is a landscape of the fusion startups just mentioned. Let me move away this little window. Here we go. So this is a matrix where you see a summary of how the 35 fusion companies are distributed worldwide in terms of technology here, row by row, and in terms of geography, column by column. You can see we are one of only 3 fusion companies in Europe, the only one in continental Europe, the only one in magnetic confinement doing stellarators. There is also another stellarator company in Japan and one in the US. And I like to categorize fusion companies in 2 big groups: those that take concepts that are cheaper, trying to make them work, as shown here, or those taking well-established concepts like Tokamak stellarators and laser fusion and try to make them affordable. And so we belong to this category, as well as Tokamak Energy, the other speaker. So some companies are pursuing reactions that have their own advantages in terms of reduced neutronics, like deuterium medium-3 or catalyzed deuterium-deuterium or proton boron. But we and other 23 companies chose deuterium-tritium because it has the highest reactivity. Of these deuterium-tritium companies, 3 are pursuing Tokamak or Stellarator with all the advantages of this well-developed concept. And we are the only one of these 3 pursuing the Stellarator with all the merits of these concepts in terms of stability and of steady state. So these, from an operational point of view of a power plant, has numerous advantages, like, for example, no past operations, reduced maintenance, simple licensing, less fatigue for the superconducting coils, also more efficient power extraction because you don't have to feed power-hungry current drive systems. So these merits and a big one, which is no disruptions, are related to the fact that stellarators differ from Tokamaks as summarized in this slide. So on the left, you see a Tokamak. You see the toroidal field coils here in blue. You see the vertical field coils over there. You see the solenoid here in the center, the plasma in purple. The field lines in black are helically twisted as a resultant of the toroidal field generated by the TF coils and a poloidal field generated by a plasma current in red, which is induced by the solenoid here at the center. So this is how the Tokamak generates rotational transform by means of a solenoid, if you want, the primer of a transformer. And here is the key difference with the stellarator. This rotational transform in a stellarator is generated without using a solenoid in the center, but rather by deforming the coils. Early stellarators used to rely on these helical coils that helically twisted the plasma and, as a consequence, the field lines. More recent stellarators replace these sets of toroidal field coils and helical field coils with so-called modular coils, which I'm sure you have seen in some pictures from Mendelstein 7X. These modular coils were originally introduced as engineering innovations to avoid the very large helical coils, but they opened a big space of new stellarator configurations, basically paving the way to stellarator optimizations to configurations of very high confinement comparable with tokamaks. So stellarators have reached tokamak-like confinement. They are simple to operate due to the steady state that I just explained. The lack of plasma current removes various issues associated with that in tokamaks, such as disruptions. So, and a whole class of current-driven instabilities that stellarators are immune from. The only Achilles heel of stellarators is that they are difficult to build. These modular coils are difficult to build, and this is in fact one issue that we tackle. In fact, the main issue that we tackle at Renaissance Fusion. In the funnel that you saw before, as we were going down and explaining how we came up with this idea of making a deuterium tritium stellarator company, I was listing all the advantages. But as you go down in that funnel, at every choice, there are also challenges or issues. So if you adopt deuterium tritium, you have to deal with the fusion neutrons that induce radioactivity in the solid parts of the reactor. Our solution to that is plasma phasing liquid metal walls that absorb most of the neutrons. By relying on tokamaks and stellarators, these devices are known for being large, and we make them smaller by means of strong fields generated by high temperature superconductors, or HTS. And finally, stellarators have a reputation for being complex, and here comes our simplification. So in summary, we are working on making the stellarator reliable, accessible, maintainable, inspectable, publicly acceptable, easier to license by means of liquid metal walls, smaller by means of high temperature superconductors, and simpler. Now, simpler here means two things, simpler HTS manufacturing and simple coil winding surfaces. Let me, so this is just an illustration of how dramatic the miniaturization can be. Let me start by explaining our innovative technique for simplified HTS manufacturing. And for that, I need to start with the traditional technique of HTS manufacturing. So normally people take tapes, similar to tapes in audio cassettes, for those of you who remember that. So these tapes go back and forth in various machines where they are coated with various layers by chemical and physical vapor deposition processes. The important layer, by the way, is the one here in black, REPCO, rare earth barium copper oxide. All the others have other functions. Then these tapes are combined in cables. These cables are wrapped around to form a coil, and in the case of a stellarator, this is a non-planar coil wrapped on a non-planar table. These coils, by the way, are fabricated with millimetric or submillimetric precision, and these are objects several meters in size. And then with submillimetric precision, they are positioned around the fusion device. So this is the traditional way. We bypass the concept of tape and cable at Renaissance Fusion, and we directly deposit the coils on the vacuum vessel as follows. So we have two machines instead of 7, one for physical vapor deposition, depositing some layers, another for chemical vapor deposition, depositing other layers, in fact, multi-layers. So in our stack, there is not only one, there will not be only one REPCO, but several REPCO layers. So this in itself is already an improvement. The process is much faster. So the result of this deposition on cylinders is a cylinder that superconducts in any direction, in principle. But since we want the current to follow a specific pattern, what we do is with a laser, we engrave this cylinder. Effectively, we draw a printed circuit on this cylinder. So these corrugations will guide the current on these cylinders, such that an array of several cylinders generates a stellarator field. Notice that the 3D geometry or the 3D, let's say, shape of the coils has been replaced by two 1D manufacturing processes. So the rotation of this cylinder, which is a 1D movement, and the scan of the laser left and right, which is also a 1D movement. this technique has advantages also for other technologies. At the end of the day, it's a gigantic superconducting printed circuit, and for different applications, different magnetic applications with different magnetic geometries, you just need different corrugation geometries, as illustrated in these videos for medical imaging, energy storage. You can even make tapes if you want. You don't just engrave on the surface, you cut all the way across the cylinder. And applications, of course, to electric motors, generators, and magnets for accelerators. Why is this relevant to stellarators? Because the coil winding surface, the surface shown here in blue, to which the coils belong, historically has become more and more complicated, conformal to the plasma boundary, shown in yellow. Conformal here means just parallel and expanded. For good reasons, by the way, because obviously higher order multipoles decay more rapidly with distance. So by adopting a close-fitting coil winding surface, you avoid the issue that by being too far, you need a lot of coil shaping for the same amount of plasma shaping, which is good. The problem is that now these surfaces and as a consequence, the coils are very complicated. Historically, coil winding surfaces were not that complicated, and so in a way, we think we can go back in time. We think that some simplified surfaces can be more than sufficient. In particular, piecewise cylindrical surfaces, excuse me, which enable this idea of the patterning directly on the cylinders. And here in the next slide, you see a comparison of the performance of this conformal coil winding surface on the left and the piecewise cylindrical on the right. So what you see on this axis is a metric of the complexity on the surface. So not surprisingly, adopting a simpler surface, cylindrical versus conformal, results in higher complexity on that surface. In some sense, where rather than adopting a complicated surface and simplifying the pattern on that surface, we prefer to adopt simple surfaces and therefore simpler manufacturing, in our opinion, at the expense or more complex patterns on those cylinders. At the end of the day, what this means is that on those cylinders, let me go back one slide or two. On those cylinders, you will need a more complicated zigzagging than the one you would have with 3D surfaces like the one in blue. That's it, but the laser doesn't care about it. And this is for surfaces that have been constructed by trial and error, let me say, but with the numerical optimization, we can do even better. So we stop the neutrons. Liquid metals fall from the top of the cylinder, and they are forced to flow along the walls of the cylinder by means of Jacobi forces that they are pushing it pushing radially outwards along the cylinder. Because we have a strong B for free, of course, so we just need to apply a relatively modest J in that flow by means of electrodes. Let me try to play this video and let's see. Yes, I hope you can see it. I hope so when we turn off the system, the liquid metal detaches from the cylindrical substrate. This is gallium indium tin, and it's a small cylinder of 60 centimeters diameter, but the basic principle is there. And this is a 1 centimeter thickness. I should say that the thickness needed in a fusion device is of the order of 40 centimeters. This is for reasons of stopping the majority or vast majority of the neutrons and the energy that they carry. So by this liquid metal flowing wall, we minimize the damage to the HTS. We minimize induced radioactivity in the device and therefore maintenance and replacement. We minimize nuclear heating, requirements for cryo, maximize public acceptance because this minimizes radioactivity, regulations. So there are several advantages. And one bonus is that the extraction of tritium is facilitated. So our wall is made of lithium ion with suspended pebbles of ceramic containing lead. And why lithium hydride, you might wonder? Well, lithium hydride for reasons of making the thickness or reducing the thickness of the wall. But also it has a bonus, as I was saying. So this is the phase diagram of lithium hydride, the temperature on this axis, concentration on lithium hydride on the bottom axis, on the, horizontal axis. The liquid metal is inserted in the stellarator at 700, it warms up to 900, then it gets extracted and it needs to be cooled down. Again, we need to extract the heat. We want to extract the heat. So in the process of cooling it down, if you just cool it down a little bit further, you cross this phase transition by which lithium hydride and its chemical equivalents, lithium deuteride and tritide, precipitate. As a matter of fact, if you do it carefully enough, you precipitate only the lithium tritide. So carefully means, fine control of the temperature. And so you extract relatively easily the lithium tritide, and after that, the tritium. So I would like to say that this is not just a random collection of 3 good ideas. These are 3 ideas that synergize very well with each other. Without entering into many details, I will make only one example. The strong magnetic field generated by the HTS helps the liquid metal sticking to the wall, and the liquid metal protects the delicate HTS from neutron bombardment and damage to the crystal, which would degrade their superconductivity. This 3-pillar approach, and I think this is what I'm going to say is more general of the fusion industry. So various fusion companies are pursuing different concepts, and is not excluded, at least in my opinion, that the reactor of the future might have, let's say, the divertor developed by one company, the materials developed by another, the coils from company C, etc. So this focus that we have on HTS and liquid metals might indirectly facilitate the success of other companies which are also relying on HTS and liquid metals, or might rely on HTS and liquid metals in the future. So this is our roadmap. We have a 3-phase approach. We want to put electricity in the grid in a retrofitted power plant, in a coal or a fission power plant, dismissed power plant. 1 gigawatt electric. We are a bit unusual in that sense. If people are interested, I can explain why we are targeting such high power. How do we get there? By first demonstrating the building block of these stellarators, these cylinders. So this is our big objective in 2 years from now, to put together the HTS technology and the liquid metal technology. So this is a cylinder with HTS deposited on the outside, generating a strong magnetic field, and having on the inside the liquid metal flowing as shown before. So to give an idea, this is a 1 meter diameter, 1 meter long cylinder. Enough to start building a small stellarator. Then as we learn to build larger and larger cylinders, eventually we will build the actual power plant, also based on what we learn from the smaller experiments. So since when we will be ready with these cylinders, we want to be ready with a stellarator design. We are working on that right now, and we're modeling the stellarator right now. So we have opportunities in all 3 pillars, technological areas. Some of them are listed here. Others can be discussed if you just shoot me an email. In general, we are looking for talented, bright, energetic, resourceful people. So from any age. And please do contact me later. I think I'm not doing too well with time, so I will just stop here. But thank you very much for your attention.
Thank you very much, Francesco. Really interesting presentation. Thanks for showing this. We will keep the questions for both speakers at the end of the session. So I would like now to introduce Mike Jackson from Tokamak Energy. So Mike, welcome.
Hi.
Francesco, you can stop. you can stop sharing your screen. That would be great. So thank you.
Okay.
Hey, Mike, please go ahead.
Thanks very much. Yeah, let me try and share my screen. If it works. Okay, you should be able to see the front page. Does that look okay?
That's still waiting.
Oh.
Yes, no, it's
Okay,
here.
it should say development work in a private
Yes.
fusion company. Okay,
Yes.
good.
Thank you
Thanks.
very much,
Yeah,
Mark.
we're running a bit late, so I'm going to try and whiz through mine to get a bit of time back, so we've got time for questions. And I also realised I put far too many slides in, so never mind about that. I suppose the idea of the talk really was a bit more focused on, I guess, working for a private fusion company, really, rather than the technology and the science. But I'll try and cover that a bit as well in the time we've got. I thought I'd start off a bit about my background. Really, I did a master's a couple of years ago, and so I did a degree and a PhD several years ago. Then worked in research and development for a company that was making mass spectrometers. Then I retrained as a surveyor and worked in renewable energy for a bit, and then I was applying back for science jobs, but I wasn't getting any interviews. Because I was a bit out of date with science. So I went and did a master's at York University with Roddy Van, which I can thoroughly recommend. I guess the audience here is already doing masters, so that's cool. But then what happened was, part of my project, I made contact with Tokamak Energy and ended up getting a job out of it. So if that's what you're interested in, that's good, because that's the sort of area I'm hoping to focus in. Let's see. I'm going to skip over this stuff. You all know what fusion is, I guess. You also probably all know what tokamak is. The idea of this slide really was just to show on the right, there's an old picture of Jet. Jet's recently set the record for 59 megajoules of fusion energy for 5 seconds. And the thing I wanted to point out is these great big magnets on Jet here are copper. And that's the thing that limits Jet from going for longer than 5 seconds because they overheat. So Jet's at the Culham Centre for Fusion Energy in the UK, the Joint European Torus, and out of that spun Tokamak Energy in 2009 with about 6 members of staff. And then the roadmap on the right-hand side is showing what's happened in the past. The people that started Tokamak Energy decided that spherical tokamaks was the answer because it's a very compact, so you're shrinking down that major radius to get a very compact machine. That first one built at the top in 2013 is with copper magnets, and it was able to hold a plasma. Then in 2015, it was fitted with high temperature superconducting magnets, and this achieved pulse lengths of 29 hours. So that's because those high temperature superconductors aren't overheating. So that was called ST25. It has a major radius of 25 centimeters. And then we went on to build ST40, which has a major radius of 40 centimeters. And you should be able to see the picture there of in 2019. There it is with some copper coils on. In the meantime to this, we also developed some high temperature superconducting magnets. There's one there that got a 26 Tesla field. And the reason that we're interested in that is because of the equation on the left. The fusion power there is proportional to B to the 4, so you get a high magnetic field from your high temperature superconductors, and you get more power, and you make it a spherical tokamak, and it's smaller, so it's easier to build and it's quicker to build. This is our roadmap, if you like, to produce. We've already done ST25 and ST40. We've just announced we're going to build another one called ST80. So that's what the job is now. Here's a bit of the science, not too much. I thought I'd put this in because it's interesting physics. This is called merging compression, which we've done in ST40, where you set up 2 plasma rings going around your donut, if you like, of the tokamak, and those where the field lines touch each other and cross over, they merge. It's called merging compression into one big plasma toroid, but that magnetic field energy is pushed eventually into the thermal energy, causing the thing to heat up. So this is an interesting way of getting plasma hot without using the solenoid ramp. That's interesting. And then this is just showing that we've some recent news. We achieved 100 million degrees. That was in the news earlier this year. And 100 million degrees C is about 10 keV, which is the sort of temperatures you need to be. So we've managed to get it up to the kind of temperatures we need to actually do fusion. Now I work in the diverter team, and on the right here we have a sort of cross section of a diverter. If you haven't come across diverters in tokamaks before, the idea is that if the core plasma is just leaking out its plasma, what happens? E cross B forces and other forces, generally speaking, mean that the ions go out to the outer wall and start sputtering away. Metal particles from the wall will go into the plasma and cause loss of confinement, basically. So by introducing extra magnetic fields to cause this X point and crossover, you can have a diverter down at the bottom, and the transport down this scrape-off layer, or the last closed flux surface. Well, not it's a scrape-off layer. That's the last closed flux surface. Just inside means that all the ions whiz down the magnetic field and hit the diverter, where you can sort of safely dispose of them. They're not going to go and damage your plasma too much, but it does mean that the diverter targets have to be able to deal with these really high fluxes of ions. This is a picture inside ST40, and at the top and the bottom there you can see the thing that looks a bit like a Dalek. I think that's the diverter that we've fitted inside ST40. The point I was wanting to make here is that the diverter assembly there is over 5,000 pieces, and there are 528 tiles in that. Obviously, the next machine is going to be bigger. It's going to be even more. And each of these is molybdenum brazed to a copper chromium zirconium heatsink. And actually, the engineering of this is remarkably complicated, and each bit needs a bit of research and development to get the braze right, to get the shape of the molybdenum, machining, everything else. So just to sort of illustrate the kind of complexities we're dealing with. So I'm working in that team on the diverters. Just a quick slide there to show the kind of temperatures and heat fluxes that we're going to be facing. Temperatures of hundreds of degrees and heat fluxes of tens of megawatts per square meter. That's a very challenging environment for the diverter surface. And these are the sorts of designs. These aren't Tokamak Energy designs. These are from the literature, but generally speaking, we're looking at tungsten. Molybdenum is okay. Tungsten's better because the melting point's much higher. And on the left, we have a sort of monoblock design, which is a lump of tungsten that acts as the armor that resists the plasma. And then we've got copper to take away the heat, act as the heat sink. And on the right is a kind of tile design with the same kind of idea, armored tungsten on the top and copper below. I am skipping through these, but I'm hoping you're getting the kind of idea. This is the sort of thing I've been working on myself, the erosion of those tungsten surfaces. So again, I'm going to skip through it. We do have some time for questions at the end, so we can always shout and ask me stuff. Basically, this is telling us that you're going to get evaporation and melting if you get very hot events. And the main problem is sputtering, though, if you can contain those temperatures down to the sorts of temperature we want to keep them at. And sputtering is where your incoming ions and causing enough energy to go into the metal lattice and causing ions to leave. I'm going to basically skip through all this. So during my master's, this equation on the left, my project was to write some code really at York University to predict what the sputter erosion will be. And that's the graph you can see in the bottom left, with different erosion. As the particles get bigger, of course, there's more erosion. I guess we might have expected that. And then when I finished my master's, there was 2 job vacancies in the diverter team at Tokamak Energy, and I applied for them and ended up getting one. So my job at Tokamak Energy has been trying to compare these graphs to experiment. I'll go through this slide. On the left, we've got a helium ion beam hitting a sample. You can adjust the angle of that sample. You can adjust the energy of your ion beam. And then the illustrations on the right are our graphs. The lines are the code predictions and the dots are the experimental data. So you can see the top one is sputtering yield with energy, and the bottom one is sputtering yield at different angles. And you can see that those experimental data kind of follow the trends, but are a bit bigger, a bit higher up. So that's telling us there's something that we're not modeling quite right. I'm going to skip through these next 2. This is basically more research that we've done. And to show, we're collaborating with the University of Liverpool. We've been collaborating with PlasmaQuest, which is a private company that makes plasma ion sources, the University of Surrey as well. This thing's quite cool. It's a focused ion beam, but you can erode the surface again and have a look at the structure. I just wanted to then talk a little bit about Tokamak Energy. I think this is a pretty good slide because this is shows our values, our company values, which is safety, agility, creativity, collaboration, and respect. And that might sound like a lot of corporate waffle, but it is actually. I've been working there for a year and a half now, and it is actually true. There is a lot of collaboration. It's all about collaboration. It's all about respecting each other's ideas. And the agility and creativity angle is basically we're looking for inventive people, interested people, enthusiastic people that are going to come up with ideas and not be afraid to try them out. And it's a very supportive environment. So if you come up with totally crazy thoughts, that's fine. And if it all goes wrong, that's also fine as well, because we've always learned something. Going to skip through this is all the sort of jobs that we're looking for: neutronics engineers, magnet engineers, manufacturing engineers. That's there's a lot to get in. I'm in the sort of development engineer box here, but I've specialized in the diverter development, so there's a further specialization, I guess. And this slide is just to show that there is a scarcity of skills. We have about 30 open job vacancies at the moment. There's a certain lack of diversity. Male-female ratio is a bit off in engineering in general. We've got a very diverse team. In the team I work with, we've got a person from Russia, one from the Czech Republic, 2 from Spain, 1 from Sweden, 1 from Malaysia. So we're very sort of diverse in that respect. But that's the whole point. We need more and more people with diverse and interesting backgrounds to come and join, really. And so I'm going to finish off because I'm conscious of the time. I said I'd try and do it quick, but I'm not sure I've done it that quick. Basically to say we are a rapidly growing company. We've now got 220 members of staff and 30 current vacancies. That's just a screenshot from our web page and the careers page, just giving the kind of ideas. And if you're doing a master's now, you can reach out to us. We do collaborate with master's students. We supported a master's student at Liverpool University recently and a PhD student before. If you're doing a project now on, well, pretty much any of these topics, you can reach out to Tokamak Energy. You can email me if you like, or just go on our website and find who's available. And we're all pretty enthusiastic and keen. So if you come along and say, hey, I'm doing an RF project, I can put you in touch with our RF people and you can have a chat with them, and it might just turn into a job, which would be cool. That worked for me anyway. So I'm going to finish off there because I'm conscious that I've been whizzing through and allow a little bit of time for some questions. So let's finish there and allow us a bit of time. So thanks very much.
Thank you very much, Mike, for this presentation and yeah, for also highlighting the opportunities for students as well as Francesco. So just to tell you briefly that since both Renaissance Fusion and Tokamak Energy are members of FusionNet, then there is the possibility for master students to, of course, apply for the job vacancies, but also to do internships there and master thesis projects that are also supported economically by FusionNet as well. But I will talk that later during my presentation at 2 p.m. about that. So let's give now the floor to any questions. Yes, I see only one question already in the chat. So this is for Mike. So Mike, is the diverter in your STs water cooled or inertially cooled? Is it water? If it is water cooled, what is your approach to avoiding water leaks in your vessel?
It's not cooled at all in ST40. It's just relying on inertia. We have pulse lengths of half a second, 1 second, something like that. So we haven't fitted water cooling to it. We, in the diverter team, we are working on lots of cooling technology. And the idea is that when they come along and say, hey, we're going to build a new tokamak, what have you got? We should have a selection of technologies that we can then implement. But yeah, avoiding water leaks is one of the key bits.
I suppose there is also a question for both of you. I suppose that would be, do you also collaborate with PhDs in mainland Europe? Well, yeah. Go ahead, Mike. Yeah.
Maybe Francesco?
Yeah.
Well, I mean, we definitely do a Renaissance Fusion. Yes, we co-supervised a PhD thesis in France, and we have various collaborations and various. We supervised some master theses, one with EPFL in Lausanne, one PhD thesis, and one bachelor project with the Università della Tuscia in Italy. So a couple of projects with Istituto Superior Tecnico in Lisboa, Portugal. So yeah, we do collaborate on PhD projects as well as masters, bachelor, or kind of postdocs or kind of formats in Europe and everywhere in the world, actually.
Yeah, I think it's the same for us. We support PhD students and non-European ones as well. It can be challenging sorting out visas, but can take a long time. But yeah.
Very good, thanks. Then there is one for Francesco. Can you reproduce the stellarator magnetic fields with the same level of detail using the cylindrical coil approach?
Yeah, in that plot that I showed before, I was showing an accuracy of 1 part in 10 to the 3 for the magnetic field. So we need to arrive to 1 part in 10 to the 4. We do have some initial results for 1 part in 10 to the 4. We are further improving that. So the way by which we think we will achieve that is by using non-circular cylinders, so prisms of non-circular cross-section. But yeah, those plots that I showed before, if I want, I can show the correct slide. If you give me 1 second. Sorry about that. So this slide that I showed in a little bit of a hurry was actually showing the color coding tells that these points have field accuracy of 1 part in 10 to the 3. So for Weinstein, for example, they achieved 1 part in 10 to the 4. In a particular way of defining delta B over B. I prefer not to enter in excessive details, it might take too long, but yeah, we think with numerical optimization we will get there. Thank you.
Thank you. So I'm going to take one last question because yeah, we're moving out of time. So there is one very interesting I find here. So I think it's for both of you as well. So how does private industry balance the need for knowledge sharing to advance the fusion industry with the financial pressure to make advancements proprietary? So how do you combine that? Because I mentioned the funding you receive, and that's also from private investors. So how do you cope this relationship?
Well, for us, there's quite a lot of stuff that is common. Tungsten services are pretty well known, and so we rely on research that's done from the public sector, and we also publish our own data that we've got. So that stuff I was showing is being published in a scientific journal. But certain things, if we identify something that's a key invention, you patent it. And that will give you your, an income stream in the future. I'm sure Francesco noticed on his presentation, there's certain things patent pending. We're exactly the same. Certain things are patentable and hopefully will generate an income stream in the future. But an awful lot of it we share, we publish, and a lot of stuff we have to collaborate. Like if we're collaborating with Liverpool University or whatever, we're going to be ending up doing agree to publish this data at the beginning. So that's kind of how we work.
Any comments on this, Francesco? Yeah.
So from Renaissance Fusion, I can say that the two aspects can definitely be reconciled. We do reconcile them. At the end of the day, as far as you patent first and publish later, everything is happy. So the investors are happy because the company is making its advancements proprietary. The scientists and engineers in the company are happy because they are publishing and they're sharing with the rest of the community. The rest of the community is happy because they learn about what we're doing and they vet and confirm the technical credibility of what we're doing. So it's a win-win situation where there is this misconception or this concern sometimes that working in an industry discourages publications or sharing with the rest of the community, but that's not at all the case. And I should also make a distinction between IP in the sense of patents and IP in a more general sense. So even after you patent your invention, there are so many little details that come from experience that do not quite appear in the patent or in the publication, but make your company give you a competitive edge over the other fusion competitors. So yeah, I hope it answers the question.
Yeah, I think to both of you, thank you. So thank you very much, Francesco and Mike, for joining this session, for showing us and the students the developments on your respective companies. We also encourage the students present to contact Francesco and Mike and contact Tokamak Energy Renaissance Fusion in order to see what possibilities you have to be there. And also, you, as I mentioned earlier, you will have also the support of FusionNet in doing this. So yeah, thank you so much, and we continue with the session. I will give floor now to Luke, please.
Yes, thank you. And we now continue with the parallel sessions about science and engineering. And in this room on the Gather.town and Zoom, Aaron Ho will give his presentation about the complexity of modeling a tokamak plasma. I think also with some surrogate modeling included. And in the other room on Gather.town, the room 2, Elisabetta Carella will give a talk from CMAT, and she will talk about materials and especially the effect of breeder corrosion on structural materials and its effect on tritium permutation. So choose which one you think sounds most interesting, but I would definitely recommend, checking them out. So hopefully see you here or in the other Gather.town room. And if you would like to join the other Gather.town room, you can just leave this meeting, walk around in Gather.town and join the other meeting again. And welcome, Aaron.
Hello, Luke. Should I start immediately or should I give some time?
I think we can wait 1 more minute for people to make up their mind if they want to stay here or go to the other talk.
Sure, no problem. Just let me know.
Yes. Okay, it appears that the number of participants has stabilized. So, Aaron, the floor is yours.
Okay, so let me share my screen. Oh. Give me a second. For some reason, it's not finding. Hey, everyone see this?
Yes, we can see your slides.
Okay. So yeah, okay, I'll just get into it then. So welcome everybody who is here to join me on this presentation. So I'm here to present to you a bit about the complexity of modeling a tokamak plasma, all the different components that are involved, and all the physics that gets put in there. We won't go into too much detail, but we'll talk around what is involved in doing such a task. But first, I'd like to tell you a little bit about myself. So my name is Aaron Ho, and I actually come from Canada, so I'm not European per se, but I've made my way across the ocean and now find myself in the Netherlands at the Differ Institute. I did my bachelor's in nuclear engineering, so nothing related to plasmas at all, more related to the fission reactors actually, but decided that, fusion was the thing for me to try and investigate. So I came over to Europe and joined the Fusion EP Master Program. I don't know if any of you in the audience are part of that program, but if you are, it's good to know that the program's still going strong. And then from the master's program, which I did 1 year in Germany and 1 year in France, then I moved to the Netherlands where I am now and did my PhD on the title Development of Neural Networks Towards Predict-First Plasma Modeling. So my career has always been sort of related to codes and doing predictive analysis of large machines. And now I'm currently doing a postdoc at the Differ facility on model validation. But all of this combined hopefully gives you enough credibility, enough convincing that I have the credibility to tell you about tokamak plasma modeling. And so we'll get into that. So why do we need tokamak plasma models? Well, for starters, if we just look at what's coming up now, there's ITER getting built, and then soon there will be a demo. And demo will, of course, be split maybe amongst the different members of ITER, and so they'll have one design per member. But in order to design these machines, we're going to need better codes to sort of analyze what the plasma in the machine is doing and how the machine interacts with it, and so on and so forth. And this is because as we move up in fusion power and as well as the input power of the machine itself, these machines get extremely costly. And all of that combined means there's higher consequences for any failures in the machine. So we kind of have to know what's happening in the machine before we run it or construct it or anything like that. Or at least we have to have better confidence that we understand it well. And on top of that, because fusion is at the moment still designated as a nuclear technology, there are regulations that may require proof of safety for the device before you even are able to build or run it. And so this involves a lot of modeling and a lot of number crunching to provide the correct safety measures and demonstrate to the regulators that the correct safety measures are in place. And then even beyond that, if we go beyond the necessity part, there's interesting work in optimization and control applications for the reactor itself. As you know, once it gets very large and very powerful, then using algorithms to try and control the plasma are going to be more and more important and harder to do even. And so these applications will benefit greatly from having sort of a digital twin in order to do all the testing and development for optimized scenarios and for controller design. So this is just some of the background of why having such a model is extremely important for our community. But then what exactly are we talking about when we talk about a tokamak plasma model? Well, firstly, mostly it's going to be considered what we call plasma transport. And so in a very basic sense, if we take our magnetic donut shape, in theory, the charged particles should be confined by the Lorentz force and not be able to move perpendicular to the field lines. But in practice, other mechanisms inside the plasma appear when we put enough energy into the plasma that enable the radial transport to still happen. And so even though the very, very basic physics says that we should not have plasma leaving the donut, we do. And that process of plasma leaving the donut is what we call plasma transport. And it effectively defines the core plasma conditions that we can achieve. So that's the density and temperature at the very core of the plasma, which is effectively where the fusion reactions occur, because that's the hottest and the densest part of a tokamak plasma. And then there's the heating and fueling, which is sort of how we interact with the plasma externally from the external world in order to basically maintain a steady state plasma in the center of the magnetic cage. And so all of these components are what we consider to be part of plasma transport. And so if I were to draw, let's say, a very basic structure of what we're talking about, let's say we have just a finite volume and it's in a 1D geometry. So things can only travel in one direction, more or less. And we want to count how much is inside that volume. Then we can say, well, in the 1D geometry, there are things that can enter and leave the volume. And then there are things that may spontaneously be created or destroyed in the volume. And so here's just some mathematical notation, but we can say that if we want to quantify the rate of change of this quantity in the volume, then it's just the summation of the net transport, the net flux that goes in and out of the volume, plus the net generation. So what is spontaneously created minus what is spontaneously destroyed. And this can be written in a very neat equation, a very simple equation, as we shown here, with the color coding to help you understand what each term means. Now, of course, this is extremely simplified, but it is what we consider the 1D transport equation. This is also called the continuity equation, also called the conservation equation. Some people even call it a fluid equation because it's dealing with fluid quantities, but they all really mean the same concept as far as plasma transport is concerned. And then to add a bit of complexity on top of it already, we need one of these equations per fluid quantity. So this would be density or temperature or bulk momentum. And then we need to duplicate it again for each let's say each species in the plasma. So this is the electrons, the deuterium ions, the tritium ions, and then all the impurities as well that may be present. So this quickly escalates in the number of equations that we have to solve for a simple even 1D transport problem. And of course, once we add multiple species, then we add cross-species transfer terms, which is like electrons interacting with ions, ions interacting with other ions, stuff like that. And we usually stuff that into the net generation term, but that's just semantics. The fact is we still need to account for them. And then, so this equation I give you here just kind of gives you a very brief, let's say, overview of how we would look at a plasma transport problem. Is basically just a balancing equation of how much is being moved from a volume and how much is being created from a volume, and then how much is just accumulating in the volume. But of course, I painted a very, very, very simple picture because each of these terms, there's only two in the equation, that is actually a collection of a number of different phenomenon, plasma physics phenomenon, or just normal kinetic transport phenomenon. And those each have their own codes and ways of calculating them. And of course, the actual numerical value that is computed by these phenomena, by calculating the physical equations that govern these phenomenon, may depend on the values itself. So it may depend on the density and the temperature, and may depend on these quantities for other species, and etc. So it becomes very, very quickly a nonlinear system, which is intertwined and intercoupled. So while I've kind of laid out a very simple problem, once you get into the details, into the weeds, it becomes extremely complicated to keep track of everything and to make sure that everything connects well, because there's also different orders in which different time scales, different length scales in which all these phenomena behave in, and then making sure you account for all of that inside your numerical model gets quite interesting, let's put it that way. And on top of that, there's also gaps in the theory. So there are certain physical phenomena which we don't fully understand yet, or at least it cannot be fully explained from what we know from the equations that we have already at our disposal. And so the research usually results in phenomenological models, which are just specific models designed to describe this one observed phenomenon, maybe not from first principles, maybe empirically, but it's describes only this phenomenon. And then that you have to somehow translate that into its meaning for a transport equation before you can include it inside a model which does the transport does the solution of the transport problem. Right, and so one example of this is the pedestal itself. And for those who are unfamiliar, we'll talk about it a bit later. But so now you have all these different codes, all usually describing its own, small specialized portion of the plasma physics, and we have to integrate them all together into basically one giant code which solves the transport problem. And this we call an integrated model. And each of these components we call sometimes modules, here in the italics. And this process of combining all the different codes together combines the physics domain knowledge that is required to understand the code itself and how it interacts with the plasma, as well as a fair amount of software engineering, because there's oftentimes numerical issues or certain parameters are not quite lined up. How do you do the connection of the different numerical schemes so that they're consistent with each other? All these sorts of things kind of pop up, which are only when you try to integrate a model into a bigger framework, and generally don't appear when you're developing the specialized code itself. And so these considerations become important and very difficult to handle if the code was already designed a certain way and you have to somehow, jerry-rig it to fit into the bigger framework. And these creates a lot of frustration, of course, but also is an essential part of this framework development. And so consistent solutions, after everything is put together, still requires a lot of iteration. So as you can see here by this diagram, that you solve all of the independent modules, and then it goes back to the transport solver, which then computes plasma profiles like density and temperature profiles. And then that has to go back into all of your different modules. And that loop is repeated over and over again until you reach sort of a converged solution. And this means that each of the modules themselves have to be sufficiently fast and accurate, because without the accuracy, this iterative process will diverge into solutions that don't really make any sense. But it also has to be fast, because if you're iterating hundreds, thousands of times, and even if one module takes, half a day to compute, then you're talking about, 500 days, which is an enormous amount of time if you want to just simulate a few seconds of plasma. So there are a number of these frameworks already existing. I give some names here. The one underlined, GenTrack, is the one I'm most familiar with, but I have heard of these other ones, Métis, Astra, ETS, CGyro, Topics. They are all from different ITER members, let's say, and they all perform, I would say, adequately similarly, but I'm most familiar with GenTrack, so I will be focusing on that one as we move forward in this talk. So how GenTrack does this iterations is it does a explicit time evolution, so that basically we just evolve the plasma in time until steady state conditions are achieved. And you can see an example of one of these simulations that I've performed here, where we start with an initial condition and we just kind of let the code compute with all of the different components until it reaches sort of a flat response at the end of the time evolution. Of course, this is not the only way to run the code, because once you have an explicit time solver included in your transport code, then it opens up applications to study dynamics, so non-steady state plasmas. And as you can see here, there's work done by Florian Kokel, who kind of modeled sort of the full plasma, let's say, discharge from the ramp up into an LH transition, then the flat top here, and then the ramp down, moving out of H mode. And this is pretty much a full discharge from build up, creating the plasma, then putting the power into the plasma, reaching this H mode, which is the high performance regime of the tokamak plasma, and then ramping down from there to a safe termination. And so this type of simulation is hard to put together because of the number of modules and the number of concerns that you have to get all the numerics correct. But it is capable to do it, but I will say for certain that it's definitely not routine. It still takes a lot of effort to put together one of these simulations, even though the code has the capability. So we're moving in the direction of trying to make it more routine and try to understand the different settings required to do this simulation, but it is quite difficult to do still. And so once we have all this together, when you run a simulation, it's really great when it works because it's quite complicated and you get to see how the plasma evolves in time and even compare it to the experiments themselves, because most of the diagnostics inside a fusion plasma device measure these quantities, these fluid quantities, either density or temperature or flow of different species, etc. And then you have a more direct comparison of the physics modules and what is actually occurring inside the machine. And so you can see here is a bit of a study I did for a plasma ramp-up scenario. You can see the profiles predictions, which is the solid line, compared against the experimental data, which is these gray points, along with the experimental error bars. And it performs quite well, considering the complexity that is inside the simulation itself, all these different modules that are connected together, where the numerics is often sometimes not super stable, and as well as having a lot of non-linearities in the plasma description itself. It's quite surprising that it can work, right? And so then once you have these simulations set up, then we can use the model to help explain experimental observations. Like in this particular example, we can see that the temperature starts going down a little bit in the central core as the time evolves. And the experimentalists were curious why this was happening. Of course, they had pretty much an idea based on all of their experiments and measurements, but it was nice to elucidate exactly the mechanism that is causing that to happen. And in what we found is that there's basically with the ion temperature changing, that you get more impurities flying into the central core, which then just causes more radiation and causes the core temperature, electron temperature to drop. Now, that's not something they had measurements for, the ion temperature. And so it was really nice for the model to be able to provide that information to them. And if we trust the dynamic simulations that come out of this code, then we can say that we do a predict first type of exercise, and then the results can be used to help experimental design. So sort of design the next discharge if you want to improve, let's say, the plasma performance or achieve a certain feature inside your plasma profiles, then these codes can provide a relatively cheap way to design that experiment based off of all the physics knowledge that we have. But of course, as I said before, it's great when it works, but it's also very, very frustrating when it doesn't. So here we have a different simulation where, just due to some numerical nonlinearity inside the turbulence code, that the toroidal rotation profile just starts flying up, and it just keeps going higher than this as we evolve the simulation further and further. But what happens because of that is that it basically stops all of the turbulent transport in the simulation, and the density starts also increasing to extremely high levels, like higher than we've ever seen inside the device itself, which means that, okay, this is probably unrealistic. And to this day, we're sure why it happens in terms of what is the mechanism that is causing this runaway effect, but how do we make it robust so that it doesn't happen when we don't want it to happen? That's a bit of a numerical trick, which isn't super robust. So this kind of tells you that there's still sort of solutions that we apply inside these models, which are basically smoothing effects or multipliers to different physics coefficients. And it adds a heuristic element to choosing the appropriate model settings for running an integrated model. And that's why getting these models to be run routinely is still a work in progress, because we need to gather more statistics on running the models for different types of discharges, different plasma regimes, even in different machines, and validating the code to their data in order to set these heuristic components to have a recipe that is easy to follow. But then, of course, I think there might be someone in the audience that says, okay, well, these fluid equations are also derived from something more fundamental, which is the distribution function itself. And so why don't we just simply evolve the distribution function? I think there is a code, Yorick, that does it, but not for turbulence yet, only for MHD. But the main problem with that is that such an approach is infeasible in practice. And this is what leads to the specialized module development in the first place, because if you wanted to do such a calculation of plasma transport with the fundamental, let's say, distribution function equation, then it would take way too much computational time in order to actually get a useful answer out of it, or an answer that is meaningful for whatever studies that you are attempting. So there's always a trade-off between the speed and the accuracy of the model, and arguably the complexity as well. So useful predictive capabilities for inside integrated models demand both of them, right? And so this is a dilemma, because if the trade-off is always there, then aren't we limited somehow in how far we can progress? And this is where a little bit of cross-domain competencies come in very important. So there's three, at least to my discernment, there's three different ways that we can figure out to solve this dilemma. And the first one is just numerical, having better algorithms that are, more efficient at computing solutions to various, let's say, physical equations, and different computational schemes which kind of take advantage of the time scales or the length scales inside the physics problem itself. This can be always be improved, and there are continuously developments in this field which can be applied to our integrated models to make them faster, without let's say, compromising on the accuracy. Then there's, in the physics domain as well, we can do model reduction and simplification. So we can take, similar to how we develop specialized modules for specific physics, that we can do such a thing even further and kind of refine, let's say, limit the domain of applicability of the code and refine how fast it takes to compute. But then it becomes limited to only that region of, let's say, physics parameter space. But that should be fine if we are only interested in looking there. And the third one is a data-driven approach, where we take a large amount of data and do statistical regressions, and perhaps even go more advanced and do machine learning on it. Now I'll go into an example for each of these three. In the GenTrack code, there's this adaptive coordination of the time step and also the call frequency of the different modules. So the user can use their domain knowledge to set the call frequency of different modules. And you can see here, let's say, an example as the plasma simulation goes in plasma time, that the different modules are called at different frequencies. And then also, there's an adaptive time step that is based on the predicted change in all the profiles, which helps to resolve large transients. So if we have a pellet module in here, which is just launching this, bead of hydrogen ice, let's say, into the plasma, which ablates and then fuels the plasma, that is usually a large perturbation to the plasma itself. And once we call the pellet code and say, okay, insert this perturbation, then the numerical algorithm already figures out, okay, this is a big change. So let's reduce the time steps so that we can resolve the actual dynamics of this big change. And that helps a lot in terms of improving usability for the users, so they don't have to set all these different times themselves manually. Plus, also, it ensures that the codes are only called when they need to be called. And it helps to save computational time if the slow modules can be called less frequency. Now, this is not less frequently. This is not always the case. At least in the past, the turbulent transport model has been sort of the bottleneck of these integrated model simulations. And you can see here that it's being called the most because the timescales that it is involved in are usually the shortest compared to the other codes inside the device or inside the integrated model. So that already solves a problem or already proposes another problem. And so what can be done there, for example, in the turbulence models, that there were simplifications to the gyrokinetic equations that are used to calculate the turbulence itself. And they were simplified in a manner that focused on reactor relevant physical regimes. So there's two examples here, Qualiquis and TGLF. If you're not familiar with the names, don't worry, I don't expect you to be. But basically, they compute the turbulent transport behavior due to the plasma conditions, local plasma conditions. So for each point in the plasma, usually there are gradients, and those gradients drive, let's say, micro instabilities in the plasma, which grow and then create turbulent effects inside the plasma as a whole. And luckily, there's been studies that say that there are correlations between the linear behavior of these unstable modes and the nonlinear behavior of these unstable modes, which basically allows us to capture the full turbulent evolution using semi-empirical rules. And that allows the calculation of this turbulence phenomenon to be sped up like 1 million times, which is incredible, because then at least we're kind of on the order of a second per calculation, which is still too slow for the applications that I was talking about at the very beginning of this talk, but is much faster than what we used to have. And these codes are trusted within the limits of these well-characterized unstable modes. So that means that if we go too far out of bounds and look at very exotic devices and magnetic geometries and plasma conditions, then perhaps these models are not the greatest, but at least within a tokamak plasma, we know that they're quite good. And so you can see here a bit of proof that the dots are a nonlinear simulations for the turbulence, and then the lines are basically this using this semi-empirical rule with the linear calculation. And it's only tuned for one point, which is this first point in the beginning, and the rest of the trends follow quite well. So that's one way we can help to speed up the code as well. And the last one is by using machine learning. And this is something that myself and my colleague Karel van der Plas here at Differ have been working on. We took this Qualiquis code and basically tried to design a neural network that would make a surrogate of it, that would take the same inputs and compute the same outputs, but significantly faster. And so it combines the expertise of data science. So how do you collect your data? How do you work with large amounts of data, and as well as plasma physics, because you need to understand a bit of the underlying mechanisms in order to make the network work. And so one example of this is that there is a domain knowledge that turbulence is driven by saturated instabilities, which exhibit this threshold, so on and off behavior. So either turbulence is present or it's not. And so this gets translated into features of the neural network model itself. So Karel did this, which is very nice work. He defined these flux ratios, which allowed us to turn all the transport channels on and off at the same time by just tying them to a single channel. And so if that single channel predicts unstable, then all of them turn on. And if it predicts stable, then all of them are off. And that turns out to be very important once you try to integrate that resulting neural network model into an integrated model. He also found that you have to modify the cost function to prevent It's because you just have a bunch of zeros on the stable side to prevent spurious, flipping of the neural network prediction back to a positive number inside this stable regime, because that also caused problems in the integrated model. So you can imagine if there was a instability in the stable regime and somehow the integrated model in its time evolution walked close to it, then it would just suddenly say, okay, this is where I need to be, because this is what will help reduce basically stabilize provide balance in the plasma, right? So this is what provides enough transport to stop the heating systems from just heating the plasma to infinity. But it turns out that solution is wrong, because it's where the code would normally predict stable solutions to the turbulence problem. So things like this, expertise that is sort of very particular to a particular physics domain, is required in order to do this exercise well, because you can equally say, here's a large data set and throw it at machine learning, but what you get out of it may not be very useful, because it learns the regressions, it learns the statistics, but it doesn't know exactly which correlations are more important to match and which correlations are just noise or unimportant. And having the domain knowledge allows us to separate that data in a way that the important correlations are given the most focus and captured best, and the ones that are not important or the ones that are noise are even discarded, right? And so one final thing that I'm going to talk about is that with these integrated models that we're starting to move into is this verification, validation, and uncertainty quantification. So verification, just for terminology, is a comparison of simulated results against other computations. So this is comparing against other integrated models or against other types of plasma profile computations. And validation is the comparison of the simulation results against reality, so experiments. And combined, both of these help to provide greater confidence in the predict first capability of the model. And so this was just an exercise that I did myself, the bottom here. So if you have the green, which is more or less represents the experimental uncertainties, and we vary the input conditions to the model within those uncertainties, then we get this red band of model outputs. And that tells us, okay, where's the model sensitive? So you can see the density is quite sensitive to these input conditions, so is the rotation, but the temperature profiles are quite stiff, so they don't change very much despite the large change in input conditions. So this is one way we can help to understand which of these predictions are more robust and can we rely on better when moving forward to using these predictions for design purposes. So I'm going to end here, and just some takeaway messages for you guys. If you didn't follow all of the technical explanations, that's fine. These are the main points here, is that the predict first full device simulations are starting to become reality via these integrated models. And this is an incredibly exciting thing, because that means we can use these models to help us design future reactors or design experiments in future reactors with greater accuracy and greater confidence. But it's important to note that the progress we've had so far is not trivial, given the complexity and nonlinearity of the plasma physics. So putting together this model and running it properly is still a bit of a touch and go. It requires expert domain knowledge as well as a bit of experience with the model itself. There's many heuristics and empirical factors involved, but work is being done to try and remove this as we use these models for more routine analysis of actual plasma experiments. And so some ongoing improvements here. I won't read them all, but I will leave this slide up during questions for people to read. And these are just sort of things that I know of that are going on in the integrated modeling community, or at least the model development community, of how we can improve these models and basically use them in more useful manners. Okay, and with that, thanks for everyone for listening.
Thanks a lot, Aaron, for this very interesting talk, I must say. So yeah, if you have any questions, you can raise your Zoom hand or your real hand. I don't have the other videos. Zoom hand is most convenient, and speak up. There's one question.
Mm-hmm.
Yeah, I missed it at the start. Where exactly do you work? It's in the Netherlands, right? But I didn't hear you work.
Yes, I'm at the Differ Institute in Eindhoven, in the Netherlands.
Is that in collaboration with the university?
Yes, it is in collaboration with the Technical University of Eindhoven. Yes, but it's a separate institute, so it's funded by the Dutch government. But we are in tight collaboration with the university. Yes.
Okay, thank you.
Any more questions? Yes.
I have one.
Hello.
Okay. Concerning the accuracy, you mentioned that you make error bars, but if the training you have of the neural network go outside of the domain you have studied or learned, what's happened?
Yes, so I mean, this simulation wasn't done, or these error bars were not generated using the neural network, but it is definitely a concern with the surrogate models that if you go outside the training space, then they start predicting very strange values, very strange numbers, and your simulation can really diverge. That is true. We are working on different ways to actually do this uncertainty quantification for the neural network surrogate models themselves. And that way, when you run the neural network model, it provides you the uncertainty of the neural network model, which should tell you a bit more on whether it's starting to move away from the training space. And you can already use that information when you're coupling it with the big model by saying, okay, if the uncertainty is too large compared, let's say beyond a certain threshold, then we simply don't trust the neural network here and revert back to using a more rigorous physics-based model. All right.
Okay, thank you very much.
Any more questions? I think there was one in the chat. I can read it out. Do you focus only on tokamaks?
Yeah, unfortunately, yes. Personally, I focus only on tokamaks. In fact, a number of these codes that I mentioned are specifically for tokamaks. So this is sort of they assume axisymmetry. So it boils down to a 1D transport problem in the 2D equilibrium. I think there may be frameworks being developed for stellarators, which include 3D geometries, but I am not too familiar with them myself. So yes, I do focus on tokamaks, unfortunately.
Thanks. Okay. And are there more questions? Then, if not, I would like to thank you again, Aaron, for your very nice talk. And yeah, it was a pleasure to have you here.
Yeah, thanks, Luke.